term, Mosey.
Yeah,
I like it.
I'm using Mosey. So, welcome back, folks. Welcome back to me, I guess. Right? You all didn't go anywhere. I just wanted to remind folks what we're doing in terms of schedules. So we are talking about FA3 right now. Hopefully, finishing up this unit this week. Maybe not. We'll see. And then your homework is due next Wednesday. So a week and a day from now. Happy to answer questions about that if you have any. If you're like, yeah, it's not due for next week, I'm not into that yet, that's fine too. And Sam is not with us today, so Erica's going to be the star of the formative assessment.
Ooh.
So I've got it over here in a way that you don't have to scroll.
Great.
All right, just make sure your head's in the frame since you're taller than me.
I don't have to touch the computer, which last class seemed to have difficulties. So.
Screen share.
Oh, yep.
Yep. Yeah, no, so the power button is right next to the button for delete, and they kept turning off my computer during the class, which is not ideal, but we made it work. Okay, there we go. Now the Zoomers can see.
Okay, great. So, the first question dealing with different types of errors. Can anyone tell me what type 1 error is?
You're going to need to talk louder.
Okay. Can anyone tell me what type 1 error is? Yeah?
When you reject a null hypothesis when it's actually true.
Yeah. Could you give me any examples of that, when that might happen?
If we have a test, a medical test or a medicine that you want to test, and it's actually true, but it turns out to be false because of the reason that it's not bringing in significant measures, right? So that could be first type error.
Yeah, so you could say like, what's it? The false alarm or false positive, that
Yep.
type of synonyms. Yeah.
Uh-huh.
And then what about the type 2 error? I'm seeing false negative, yes. That is a great synonym for that. So I believe also could be called a miss. Does anyone remember what that case is or any examples of that?
Like having a small sample size,
Yeah.
then leads you to assume there's like no effect, but maybe there is because you just don't have enough data or enough range of data.
That kind of segues really nicely into the second question of what power is. So if you're thinking about that, like if you have that word that you were looking for, it seems like, power. So can anyone tell me what power is, or any factors that can impact power? Oh, and I see an example in the chat from the type 2 error was when you test negative for COVID, but you actually have it. So yeah, that would be very bad miss. Don't want that. I see in the chat as well, your probability of detecting an effect if it's really there. So that would be for the
Power. Yeah.
the power, yeah, okay. Yeah, because it's related to which type of error, the power.
Will it be second?
Yeah, because there's the CERN equation, if anyone remembers. Not really equation, but 1 minus b, yeah, exactly. To see the relationship between the type 2 error and the power. And then what are some factors that are going to impact power?
Sample size.
Sample size, yes. Do you want sample size to be bigger or smaller?
Bigger.
Bigger, yes.
More power.
Yes, exactly. Anything else is going to impact power? Effect size? Yeah. And for that one, do you want bigger or smaller? It's actually bigger, but good try. It's confusing, yeah. And then, because if you have a bigger effect size, then it's going to be easier to detect it, because like if your effect size is close to 0, maybe you could get harder to test like the null hypothesis to see the difference from 0, whereas your effect size is like 1,000, it's a much different effect where you could see that, detect that difference a bit better. And then there is one more thing that could affect power.
Alpha.
Alpha level, yes. And then for that one, do we want it higher or lower?
Higher.
Higher, yes. But is there a certain consequence of it being higher? Think of the errors. It could cause a type 1 error. I'm seeing in the chat, yes. So if you're increasing your power, it could mean like your alpha level, it means like if it's 0.05 compared to 0.01, you could have those times where you accidentally think that you're rejecting it and it's not actually significant. And then the last question, consider a GLM with a single categorical predictor with 4 categories, and then the following questions. Does anyone know what this analysis is called? I heard it. Does someone want to say it again?
ANOVA.
ANOVA, yes. Exactly. And then screen is totally in the way. So given a single model intercept for a reference category, how many fixed slopes would we need in order to be able to differentiate the outcome mean for each of the 4 categories? 3, exactly. And how many fixed effects would we need total? If we have 3 slopes and then we have 4 categories, if we're including the slopes and the other fixed effect in the model, 4, yes. So if we have an intercept and then those 3 of those slopes, you would have 4 fixed effects totals. And then how many pairwise mean differences are amongst those 4 categories? Yeah, I was thinking 6. And there is a certain formula, if you don't memorize off the top of your head, but if which one was it?
Permutations.
Permutations, yes. With the factorials and whatnot, I saw a lot of you.
Should take combinations. It's combinations.
One of those.
No,
Yep.
yeah, I can write it out for you.
There's a couple exclamation points, yeah. But yes, it's 6. And then how many of those pairwise differences are given directly by the model? 3, yes, because we had the 3 fixed slopes. So we're going to have those 3 directly given by the model. And then how many did we have to get by ourselves with linear combinations? 3, yeah. So those 6 total, those 3 from linear combinations and the 3 implied by the model. Am I missing anything, Lisa?
I don't think so.
Okay. Yeah.
I
I felt like everyone did pretty good on this.
Yeah, I did.
Yeah. Great job, everyone.
Great job. I just left the meeting. Okay. Otherwise, the battery on my phone is gonna go nuts. So yeah, everybody did pretty well on these. See if I wanted to add anything. I can't think of anything to add. So yeah. Are there questions that you still have after doing this review in class that we can talk about? Are we feeling okay? Feeling okay? All right, well then, I'll get rid of that. Because I had recorded a video about the quadratic stuff, I thought it might be useful to review it briefly, in case that, you had questions that you weren't able to ask out loud in a video format, which is how they work. So let me start let's go with lecture 3, slide 27, quadratic slopes. So this picture literally is going to be showing in my longitudinal class. This is where I stole it from. This is one of the points of intersection of the 2 classes. So quadratic is how you make a slope bendy, broadly construed. Bendy is my word for nonlinear. So if you have x as a predictor, and it's a quantitative variable, it has a linear slope. If you add x squared, that is referred to as a quadratic slope. And the 2 work together to create different kinds of patterns. So in this first picture on the top left here, this is slide 27 again in lecture 3, the linear slope is 4. And I have to know where the 0 value is for my predictor, which is time in this plot, in order to know where the 4 should go. So in this model, the linear slope is specific to time 0. So it becomes conditional. And this picture has a quadratic slope, so time squared would have a slope coefficient of positive 3. And if you remember nothing else, there is one rule. Before you can talk about what a quadratic slope does, you have to multiply it by 2. Cough, cough, homework question. I can give you 3 different reasons for that. One is because we're talking about second derivatives of a function, and the quadratic is actually half of the rate of acceleration or deceleration if you work through the math. The second borrows rules from interaction terms, which you haven't seen yet, so that's not going to go well. And the third is just with my mom vibe, because I said so. Right? I don't have a better reason than that. But the way it works then is if I take this quadratic slope and multiply it by 2, then it's 0.6. So I would say the slope has become more positive by 0.6 for each unit in time. So every unit change of x here. So it goes from 4 to 4.6 to 5.2 to 5.8. And the slope itself is at the dot here. So it's the best of my PowerPoint drawing ability. This is the slope of the line that is tangent to the curve. The term for it is instantaneous. So I would describe this as an acceleration because it's already growing, but it's growing at a faster rate. So where you might see this on Earth would be something like growth of bacteria on a sponge in your sink, right? The more you get, the worse it gets. It accelerates. COVID rates look like this at first, vertical asymptote essentially. The reason that it's becoming more positive is because the linear slope has a positive slope, and so does the quadratic. Question or head scratch? Head scratch it is. Okay, we'll all just scratch your heads for a moment here. It's all good. The opposite happens on the top right here because of the negative quadratic. So now they're working against each other. So yes, people are increasing over time, but as time goes on, the rate of that increase slows down. So I would call this deceleration because it's growing, but it's slowing down. We also have the same kind of slowing down. So why is it saved to this PC? That's odd. There we go. Same kind of slowing down happening in the opposite direction on the bottom left here. This is a negative linear slope at time 0 of -4. Twice the quadratic is how the slope changes per unit of x, so it's becoming less negative. So -3.4, -2.8, and so on. And then we can have accelerating. So there is, I used to work in the area of cognitive aging in addition to methodology, and there's actually a phrase that would go with this picture called terminal decline. It's not a very happy phrase, but it is the case that when older people start to experience health problems, it accelerates until, things end. So this would be a picture that would be consistent of that. It's a negative slope, but it's speeding up. And each of these is a different pattern, but one thing to keep in mind is what would happen if you kept going. So let's take this picture right here. This positive slope is slowing down. Like, where's it going to go after time 5? Yeah, I'll take gestures. Is it going to stay positive? No. No, this picture, the other half of it is right here, essentially. Right, this is the front end, and then it meets up, and that's the back end. So quadratics create U-shaped functions. The only question is how far you plot with respect to your data, and would that actually happen in the range of x that you've observed. So when it comes to something like learning, for instance, a quadratic model is very common, like in measuring learning over time, but it would predict that people eventually stop learning and then start forgetting, right? It comes back down.
But we do.
I know, well, not yet.
Sorry.
Yeah, no, it's true though. And so from a theoretical perspective, sometimes folks have issues with these models because it doesn't make sense all the time that what goes up is going to come back down. It should sort of level off instead. So that is a valid criticism, but these can be useful for capturing narrow ranges of curvilinearity in a slope. So this is still a linear model, by the way. This is just nonlinear in the variables because we have x and x squared, but they're still multiplied together as slope times variable plus slope times variable plus slope times variable. And I had gone into more details than I think is necessary in the video, so I'll skip a little bit of that. This is the example that we're going to fit a quadratic to. This is change in income as a function of chronological age. So the youngest person in this sample was 18. The oldest person was about 75, I think. And this looks like it goes up and comes back down. So this would actually be an instance in which a quadratic function seems like a reasonable guess. So the model would look like this. How many fixed effects do I have in this model? Because this was a sticking point. Is it 2 or 3?
2.
Ah. I would say 3 because I said fixed effect, which is an umbrella term because you can have intercepts and slopes as specific kinds of fixed effects. So fixed effects means intercepts or slopes. How many fixed slopes do I have? 2. There we go. Conceptually, how many variables do I have in terms of like the concept of what I'm predicting here? I would say I have 1, like I have age, but it takes 2 slopes to delineate its effect. So technically, I'm thinking of this as 1 variable, but I'm building a model that allows the slope to go bendy by adding the squared version of it. So in this model, the intercept is going to be the expected value of our outcome variable when all my predictors are 0. I've shown the centering in here so that we are, the beta 0 term tells us the expected income for an 18-year-old. What would happen if I forgot to center age? Would the intercept be the same or different?
Same.
What an intercept is the expected value when x is 0, right? So if I forget to center,
It's going to be different.
then I'm predicting income amongst newborns.
Uh-huh.
Like if I go back to the picture here, I'd be clear over here, and it would be negative probably. So the intercept adjusts to the definition of your 0 value on your predictors always. That's why I ask it as one of the homework questions, because if you get that wrong, that means you have the wrong predictor centering or coding scheme. So it was $2,677 on average. The linear slope then is the instantaneous rate of change, so at the point of your variable being 0. So it's at age 18. So in this model, it would also change if you centered somewhere else. And if you think about it from the picture here, here's my slope, like right here at age 18. If I centered, say, at 46, the slope would be here instead. It would be flat. So you can kind of picture the slope changing as you go around the curve. So it's not specific enough to say, well, the linear slope, because it could be anywhere in here. There's not just one slope. The model implies multiple instantaneous linear slopes all the way through this function. So that one, at age 18, for every additional year of age, they make about $1,200 more, according to the model. The expected inconsistency of that, the standard error, is 0.135. What's a standard error again, broadly construed? Cough, cough, more homework questions. Always. Is it a sample thing or a people thing? Start with that. Sample thing. So standard error tells you the expected inconsistency across repeated samples of that estimate, how wiggly it would be if you repeated the study. So 0.135 is how far off on average the sample slope would be from the population version. And
Only at that point.
at that point, yep. The sample slope at age 18 specifically, which is what the slope coefficient refers to. Yep. Quadratic slope then is half the rate of acceleration or deceleration. So we multiply it by 2 to talk about what it does to the linear slope. So the way that I would interpret this, change it to negative 0.04, that is how much less positive the slope of 1.2 gets per year of age. So the slope itself is slowing down, and that is as expected based on the picture here. So it is becoming less positive. Eventually it will hit 0, and then it will come back down the other side and turn negative. So twice the quadratic is what happens to the linear per unit x. And then you can figure out what the predicted income would be. So here's some examples using plugging in these numbers for the fixed intercept, the fixed linear slope, the fixed quadratic. Question?
So would the standard error on the quadratic slope actually also be doubled if you're talking about how much off you would be?
I don't think it doesn't work quite that way.
Or are you only going to use that in reference to the coefficient for that, but not for the slope itself?
So the standard error for a predicted value would be computed differently. And it would also take into account how far away from the mean you are on the predictor, because it gets wider as you move away.
Right, that's what I was wondering about that 0.003, what would happen to that, so, okay, very good.
Yeah,
Thanks.
yeah. I would say that the multiplying by 2 holds for the slope coefficient.
Only that.
Yeah,
But
there's
not the-
probably some extra
Okay.
pieces to it
Okay,
because of
very
that.
good, thank you.
Yep, no, thank you. And I got all of these things from asking the software to compute these predicted values, which is why they come with standard errors, which is nice. And then you can also predict linear slopes. So this is the advanced part. I'm not going to make you do this, okay? Because the longitudinal class has a hard enough time of it. I think maybe the first class is not the place to do this, but I wanted to show it to you. So if you think about predicting the slope itself, like if you want to know what's the slope going to be at age 50, what's the slope going to be at age 30, like you can figure that out. The model happens to give you the one at 18, but it's a linear combination to get the others. So if we start with what the slope is at 18, that's the 1.223 here, and we subtract the quadratic coefficient, I can't multiply it by 2 in the software. So instead, I have to multiply the value of age that I'm filling in. So 2 times the age that I want the slope for is how I ended up with this result. And you can do the same thing for the other ages here. And why is it 12 if I'm doing a prediction for a 30-year-old?
Subtract off 18, it's not like it.
Yeah, because of the centering. Yeah, 30 is 12 more than 18. That's how I would say that. All right. And in case you wanted to know, there is an equation where you can figure out where the slope is going to tilt over and go to 0, and it's right here. So 48.575 in this data set. Yeah, so here's what the end result is. So the fit through these individual age means looks pretty darn good. Seems reasonable. Now, because age and age squared work together, I would use the R square for the model as my effect size for this. I wouldn't try to compute partial R's for each of these things because that doesn't make a lot of sense in this context. So R square means what again? We'll do more reviewing. Zoomers, I'm watching the chat. You can play too. What's R square? Squared correlation. I'll take that. Correlation between what and what? Y is one of them. X is close, but not quite. Keep following the path. Or you can phone a friend. What is it? Not x squared, but it's how x is being used. So x does go into it, but it's not a correlation between x and y, because right now we have 2 x's. I've got age and age squared. Another answer, explained variance in the model. Yep, that's another way to think about it. So there's 2 different definitions. And one of them I think is more straightforward. R square is the proportion of variance that's been explained by your predictors. It's a proportion. So that's why it is 0.114, meaning 11.4% of all of the reasons why people make different amounts of income has to do with age. That's probably the more direct way to think about it. In terms of a correlation, so if I unsquare it, R is 0.338. That is the square between, or the correlation between Y and Y with an accessory. There's your clue.
Y hat.
There you go, Y hat with an accessory, see? Yeah, so Y hat is what the model says income should be. So if I use this equation right here, and I build myself a Y for each person in the data set, and I take that predicted Y column called Y hat, and I correlate it with the real Y, that's R. You square that correlation and you get R squared. So R squared tells you how related the predicted outcome is to the real one. Y hat, indeed, indeed. All right, let's see, yep. Oh, and then I talked about this on the video as well. If you log transform a variable and fit a linear slope to it, that creates this kind of more exponential curves. So for for linear models where you want the slope to sort of shut off, this is an easy way to mimic that. True exponential functions would require nonlinear models, which are more difficult to estimate and take a little bit more to do. Do you want to see where the numbers came from? Why not, right? Well, I'm going to make you do it, so you may as well. So I'm on page, do you want to see the linear age model as a reminder, or do you feel okay with linear slopes right now? Okay with that one? We'll keep doing linear slopes throughout the semester. So I'm adding quadratic slopes. So my previous model that had linear age only accounted for 4% of the variance, okay? And it also didn't make a lot of sense because it said as you get older and older, your income should go up and up and up and up and up, and that doesn't make sense for these variables. So if we add quadratic age, to do that in the code, the good news is that you don't need to make quadratic age as a separate predictor. In certain software packages you do, but not in these. So this right here is age squared according to Stata. The hashtag or the pound sign, depending on how old you are, creates multiplicative combinations. The same thing in R is right here. So it's capital I, then in parentheses, the name of the variable, and then a caret and a 2. That's how you can create a squared version of the predictor. This I function doesn't always work, so sometimes I do have to actually just make the squared variable to make things easier. So it's up to you. It should come out the same way either way. So I have the linear slope and the quadratic slope both, okay? The quadratic slope can only be interpreted that way if it is above and beyond the linear. Otherwise, it's going to be like the two smushed together, and it's not what you want. So in your homework, I ask you to fit a quadratic slope. That implies the linear goes with it as well. So here's what happens. We have model information, error information. Do we want to talk about these, or are you feeling okay with these? No one has an opinion. I've bolded the things that you would want to pay attention to. So model is what we know. So how much information did our model capture in our outcome variable? How many slopes did it take to do it? What is the average contribution per slope? Then how much information is left over? That's this one for error. Divided by how many more slopes could we add? So it's 731 because there are 734 people in this sample. We always have an intercept, so empty model it has down here. So that intercept takes us down 1. Then we lose 2 more for the slopes that are in our model, leaving us at 731. So what is this called, by the way? Degrees of freedom, which one? Denominator, yeah, because the F is built of model divided by error. So that's where the numerator denominator language comes from. What is my numerator degrees of freedom then? 2. It's always the number of slopes in your model. Number of slopes specifically, fixed effects includes the intercept as well. So this includes all 3 fixed effects. Then if I have known over unknown, that's my F. This is my R² value, and this is the p-value that goes with that test. So this p-value is testing both slopes simultaneously against a null hypothesis of 0. And this is how you would write that. So you will see in your homework drop-down menus that have choices like, is it F, is it mean square error, is it P, is it R²? And the numbers that you entered should provide the context so you know which one it is, but I will always have it in this order. Here are the results out of, this is R code right here. So the intercept then, that's my expected income level for what kind of person again?
18.
An 18-year-old, because that's where X means 0. My linear slope is 1.22. Is it significant? Yeah, scientific notation. So P is 0 to 16 decimal places. Decidedly significant. Yep. Is it enough to call this the linear slope of age? Or is that an incomplete interpretation? Incomplete. What do I got to add to it?
Well, it's not the linear slope of age because it's just the slope at one point.
Mm-hmm. And which point is it? 18, yeah. This is the linear slope at age 18 specifically, because it would be different anywhere else. And so then the quadratic, is it speeding it up or slowing it down? Slowing it down. So there are only 4 patterns when it comes to quadratic terms and interaction terms more generally. They can either take something that's positive and make it more positive or less positive, or they can take something that's negative and make it more negative or less negative. Once you figure out which pattern you're in, you'll know how to talk about it. So yes, as you get older, at least as evaluated at 18, you make more money, up to a point, right? So this is working in opposition. It is slowing the linear slope down by how much? And don't say 0.02. 0.04. Multiply it by 2. That's the trick. The slope is slowing down per year by 0.04. And that's funny? No?
I just said 0.39.
Okay. Yeah.
But
I'm
I do have a
having fun with it.
question.
Yeah, go ahead.
Would it make any difference to the computer if you just made a column of the squared ages and used that as opposed to using the exponent of 2?
It does not when it comes to estimating the model.
Okay.
However, in certain routines to generate predicted values, you like if you don't make the squared version yourself, if you do the hashtag or the I thing, then when you're generating predicted values, like once you tell it what age is, it will know what age squared is because it understands that they're connected because you've defined it that way. If you make an entirely separate column, you would have to fill in what you want for age and age squared because it wouldn't know that they're tied together.
That was my question.
Yeah,
Thank you.
for prediction purposes, you would have to be careful with that. But for estimation purposes, it should be fine.
Okay, perfect. Thank
Yep.
you.
Sure, no problem. And order of operations, if you're going to build it yourself, center first, then square. Otherwise, you will not come up with the right answer. Yep. All right. Let's see here. So the other question that I had is, how do I know if the change in R² is significant? So the linear model had 0.04 as an R². This model that added a quadratic slope increased the R² by 0.074 up to 0.114. Well, that's more, right? I've explained more variance, so that seems positive. That's good. Is it significant? And where do I look for that? Let me give you some choices, because I think multiple choice questions generally work better, right? Is this the p-value that tells me whether the change in the R² is significant? Because it kind of looks like it should, right? It's bold. It is bold because it's answering a different question. So this p-value says, is this R² not 0? This R² is what it is now. This p-value is testing it. My question is about the increase. And is that significant? Is this a better model after adding the quadratic than having the linear slope only? That's the question. This p-value isn't going to answer that question. Do I have that answer somewhere in here?
Mean square, the one that's not showing up on the screen?
Which one?
The 0.001?
This one is referring to this p-value right here.
Oh, sorry.
Yeah, so p is never 0. It's just printed that way.
Right.
You would always report it as less than some critical number.
Okay.
Yep. Now, is the answer in here somewhere? And if so, where? Think about what we've added. So there's a term called nested models. I don't know if we've introduced this formally. Okay, new term. A nested model is a subset of a model. So like I started with linear age. That is nested in this model because I added something to it. So like there's like dolls where like you open the doll and there's another doll inside. Like I think they're called nesting dolls. Like think of that, right? I
The
had
Russian nesting
like the
dolls.
inside is the linear one, then I have the quadratic one, and then I could keep going if I wanted to. So from that perspective, what makes this model different than the previous one?
The third row.
This new term.
Yeah.
Is this new term helpful? Is it significant? Yeah, more scientific notation. If it goes to scientific notation, it's significant. There's a general thing here. Question from the Zoomers, 0.091. I'm not sure where that number is.
Oh, it was
but,
2 rows up.
oh, 2 rows up.
Yeah,
Where's that?
in the, wait, go back down.
Oh.
It's the beta 0.
The beta 0. Gotcha. Yep, no, the intercept in this case is not significant, meaning 2 is not 0, or is not different than 0, but that's like, who cares? So this is the one line, the one parameter that makes this model different. And if the new thing helped, then the R-square has to have improved significantly. It's tied together. So another way of saying the quadratic slope is significant is saying by adding it to the model, the R-square increase it created must be significant too. There's a one-to-one correspondence. It's curious if it were beta 0. Nope, not in this case. Beta 0 is always there. So empty model always has beta 0, right? Then we add slope. We added a linear slope, added quadratic slope. So if the new thing is significant, the change to the R-square has to be. One-to-one correspondence. What do you think happens if I add 2 new things?
Test them one at a time.
I'd either have to test them one at a time, or I'd have to lump them together to test their joint contribution. That's in the next unit.
Oh boy.
Mm-hmm. Yeah, it actually might even be in this one. I may have done that already here, but yep. So yes, putting it all together. The linear model that only had this much, linear age, accounted for 4% of the variance. After adding quadratic age, the R-square went up to 0.114. If the beta 2 slope is significant, then the change in the R-square has to be significant too. All right, any questions on that? We're feeling okay with that? Cool. And then here's some code to generate predicted outcomes. So Stata, you can do this with LinCom. These are predicted outcomes for anyone who is 30, 50, or 70 are the example values. These are predicted linear slopes at those same ages. So what would the slope be at 30? If I kept following the curve, what would it be at 50? What would it be at 70? The corresponding R code using GLHT looks like this, where the first one is I need one intercept. I need to fill in 12 for the multiplier of my linear slope, and I need to fill in 144 for the multiplier of my quadratic slope. So it's squared when you're generating predicted values. If you're generating predicted linear slopes, then it's the x variable value times 2 instead. Now, can we just agree that this is annoying? Can we agree on that? I promised I would show you the less annoying version at some point, but I wanted you to suffer through a little bit of this so that you understand what the less annoying version is doing on your behalf. Fair? Okay. So let me show you a faster way. In Stata, for instance, there is a command called margins. Margins means predicted values. So I told it I would like predicted outcomes for age 18 as the predictor, and this is a range. So here's how you would read this, from by 2. Start at 0 in increments of 1 and go up to 57. That gives me predictions for every single possible age in my data set. In that much code. Okay? This much. That's it. Yeah, exactly. I love Stata for this. Quietly means don't print it, which, like, no, wouldn't it be like invisibly, right? Because I don't hear any output when it arrives. Like, it doesn't like ding at me or something. But noisily, by the way, is the default. You know what that means? Print it. I don't get it. But I didn't want to print it in the output because all I wanted to do was make a picture. So whenever you run margins, immediately after it, you have an option to make pictures out of whatever you just generated. So margins plot says, what would you like X to be? I'd like it to be age 18. You can name the plot, and you can save the plot as an image file. Because it pops up in a different window, it's not going to be stored in your log. So you have to actually take the time to hard code the saving part. Also in Stata, this one gives me predicted linear slopes at every possible age in my data set. So dy dx, derivatives. So I made those two pictures and showed them here. So this is what the model predicts income to look like. And note the standard error bars. They're skinniest in the middle towards the mean of age, and they get wider as you move away. The plot on the right is a different way of talking about a quadratic slope that I thought might be helpful, and if it's confusing, then just ignore it. The y-axis on this plot on the right is the linear slope, not the predicted outcome. So like at age 18, the linear slope is 1.2, and this is what happens to it as age increases. It changes linearly. So the quadratic is a constant force. It changes the linear slope by 2 per unit age. Oh, you like that. You're nodding. That works?
It's like the derivative of it.
That's exactly what it is. But we don't require calculus before this class, so I'm not going to call it that, but that's exactly what it is. Yeah.
That's about all I remember.
Yeah, I know. Calculus was many moons ago, so
Yeah.
it's like, I did this at one point, and I had no idea at the time why I needed to do this in my life, other than someone told me to. And had I known this was coming, I probably would have paid more attention. But in R, the plotting is a little bit harder, but the predicting is not. So there is a function in base R called predict that works with almost every other function. So the first thing that I'm doing here is building a new data set that has age as a column, and it has all the values of age for which I want predictions. So starting at 0 up to 57 in increments by 1. And that's because these are centered. So it's actually 18 to 75. I am then feeding that little data set into this function here. So the predict function says, hey, where am I getting the information to do the prediction from? Object, the model results. So I had saved the R version of the quadratic age model as something called model quad age. It has all the ingredients. And then it's like, would you like to put it in the same data set or in a different one? And I would like to put it in this one. So new data, where's it going? Would you like some standard errors? Sure, why not? Would you like a confidence interval? Okay, why not? And then plot is a generic command. There's all kinds of ways to plot things in R. I am not good at them. But ggplot and ggplot2 are the ones that offer a lot more customization. This is just a bare bones plot. So the way that it works is that you first build like the plot space, and then you insert the lines. And I had to look up all of this stuff. So I'm not entirely sure now what these things mean, other than it's a line plot. Limits, I scaled the axes, I knew that one. And I also added labels, because you should always do that. So then I'm adding lines for the upper and lower CI as well, and then I added a legend. And the end result is this little picture right here. So, bare bones plot. But if you're like, yeah, I think that plot looks ugly, but I don't want to take the time to learn how to plot better, you know what you can do? Take the predicted outcomes and go export them into Excel or Stata or your program of choice. You can make plots anywhere. It's generating the predictions that's the tricky part. And I'm not going to make you do this either, but because you would want to do this in life, I wanted to show you some code. And this picture I made in SAS, by the way. This is a little more involved, but I wanted to show how the predictions actually held up. And here's my little paragraph. It's a little paragraph compared to an entire results section, but it's
Or
a
an
long
entire journal article about it.
Yes.
So,
All right. Any questions on quadratics? You can now do your entire next homework 3. Hooray! No, just think of it this way. You can be productive while putting off other things if you start your stats homework. And I know this because I do the same thing. Guilty as charged. All right. How about a different kind of nonlinear function? We talk about piecewise slopes. These are also known as linear splines. That's another term that you may have heard. So piecewise slopes are useful if you're thinking of the range of x as discrete sections. So I used it for this example because we all know that a 1-year increase in education does not give you the same bang for your buck, right? If you make it to 8th grade versus someone who makes it to 9th grade, they are still not a high school graduate, and they will be qualified for the same kinds of jobs. Versus if you do make the jump from 11th grade to 12th grade, you can expect higher income than someone who hasn't graduated high school or received a GED. And then I think the same thing happens here, right? You know the term ABD that we're all hoping to be at some point, right? That means you've passed your comps and that you've done with everything. That means nothing if you don't actually finish your dissertation. ABD is not a thing. Like, that is not a recognized category. It is recognized while you're in school as a milestone, but you have to actually finish the dissertation to have it count for something. So that last year is really, really important in that context. Oh, and by the way, a little professional development. Have you heard the story? There's only 2 kinds of dissertations in the world. Have you heard this yet? What are they? Done? Not done. Those are the 2 kinds. That's it. Nothing else matters. My dissertation was like a complete piece of crap that I had to redo almost every part of so I could publish it. But I did that as a postdoc, making 3 times the salary of what my stipend was. So done or not done, those are the only goals. It doesn't have to be perfect. It just needs to be done. And you will look back on it someday, even if you did think you did a really good job, and be like, oh, that wasn't as good as I thought, because that's what happens as you keep going. Anywho, piecewise slopes, because 1 year of education does not mean the same thing. So to me, just eyeballing this plot and also taking into the context of this variable, everything before high school, I think, is sort of one flat line. And these points out here are noisy, but there's very few people that are in these categories. So there would be huge error bars around these points. There is what appears to be an acute jump from 11th grade to 12th grade in terms of income. And then there's whatever this is after that. So this is arguably should be nonlinear, but this model is complicated enough, so I'm going to fit 1 slope here, 1 slope here, and 1 slope here. So where these models would be useful, again, in a longitudinal context, if you do multiple baseline intervention designs, so like if you have a baseline period where you're observing someone, and then you do something to try and make them better in more observations, and then you take that thing away and see if they go back down, and then you bring it back and see if they go back up. Like, those are discrete sections of time where you expect different things to happen, and this model would fit directly onto that. Another instance would be like if you have some kind of clinical measure, let's say that you have, what is it, any psychologists in the house today? No? 1? Okay, can you give me a clinical measure that has some sort of number that means something? I am a psychologist, but I'm not the right kind.
I mean, you could do like the Beck Depression Inventory.
What's the magic number that makes you depressed?
So some inventories have 10, but let's see. I'm gonna look up the most current.
Okay, I'll go with 10, and then you can correct me.
Yeah.
So you might have like subclinical depression versus clinical depression, and if 10 is the magic number where that dividing line happens, then you might want to see, does more depression relate to whatever in the subclinical region, and does more depression relate to whatever in the clinical region? Like,
So
that
it's
would
63. I was way off. Sorry.
63?
It's been a while since I've
63 is a
Beck
very
Depression Inventory
specific number.
63. Yeah.
63. Okay, so
I'm thinking of anxiety. Sorry.
no worries. I didn't want to be wrong, but there's a lot of measures that have some magic number once you cross it. So my son, at the end of the year, he takes, whatever the Iowa Test of Basic Skills is called now. It has a different acronym. And like they have, proficient, advanced, like meets expectations. Like they have all these categories that they divided a continuum into. So if you wanted to see, does more math relate to whatever in the proficient range? Does it still relate to whatever if you go into the advanced range or whatever it is? So in quantitative variables that have these kind of benchmarks, oh, I got a whole thing. 0 to 9 is minimal, 10 to 18 is mild, 19 to 29 is moderate, and 30 to 63 is severe. So if you wanted to look at what more depression relates to, how many slopes would that be? Minimal, mild, moderate, severe. 4. Yeah, you could carve it up into 4 sections and look at the effect of more within that region. So that's what these models are for, broadly construed. So I've got 3 slopes here. Now the tricky part to this lies entirely in setting up your variables. The interpretation, once you have your variables, is exactly what you're used to. The slope says a 1 unit change in x relates to this much change in y. So here's how it will work. For this specific example, the coding will always depend on exactly what you're trying to do. But here I have possible values of education starting at 9, going up to 18. I need to create 3 different slopes through these sections here. The one that is going to cover grades 2 through 11, I'm going to name less HS, less than high school degree. The slope that covers the transition from 11th grade to 12th grade is grad HS, and then over high school. So I'm building 3 new predictors that are going to replace years of education in the model. First question is, well, where do I want my intercept to be? I have to zero out all of these new variables where I want the intercept to be my reference point. So I'd put that in yellow here. I decided grade 11. Completely arbitrary, but I figured why not? So then the first slope, less than high school, keeps track of the change in education up to that breakpoint. So if 11 is my reference, then I would code 9 as -2 because it's 2 grades below 11. And grade 10 is 1 grade below 11. Now I only want this variable to keep track of the folks who got up to 11th grade. It's irrelevant for the others. So that means I zero it out the rest of the way down. So if all I had in the model were this, it would be like a 1 flat line and then 1 line like that. Okay, so this slope is capturing everything below 11 and then it shuts off. The next slope is capturing the acute difference between 11 and 12 only. So it's 0 before we get there. It switches to 1 once we're in 12th grade, and then it's going to shut off. But it has to shut off where it left off. Otherwise, it would put us back down to 0 again. So it stays at 1 so that it doesn't index any further changes in education because it's only capturing this one little jump in the middle here. Then the last slope is only relevant for folks who graduated high school, who have some sort of graduate degree or additional years of education. So it's not relevant for 9th, 10th, or 11th grade. And 12th grade is already handled by this one, so it picks up where this one shut off and indexes the further change in years of education. So it's coded 1 because 13 is 1 more than 12. So each of these is relative to each other as to where it picks up, it starts, and then stops. So I think your homework, the next one, this is going to be homework 4, I believe, has only 2 slopes. It's a 2-slope problem instead of 3, because this is hard enough. Okay, stare at this for a second. Does this make sense? Just each one is doing its job in its range. It's 0 before it starts, and it shuts off wherever it left off. So here's what's going to happen. So now I have how many fixed effects in my model? And don't say 3. Fixed effects. 4 in total. We got to count the intercept as a fixed effect. How many slopes do I have? There you go. And I didn't have a centering convention in this equation. I used the names because that would require like a couple sentences to describe the coding scheme. There's no easy way to denote that. So I have 3 slopes, so that means my numerator degrees of freedom is 3. And then n minus k for the number of fixed effects. There's 734 people in total in this data set, so I could add 730 more slopes. My f is 47. Does that look good to you? 1 is the neutral point for f, where you know as much as you don't know. Like the ratio is 1. Yeah, so P less than 0.001 for this, so yes, the F is significant, meaning these three slopes work together to significantly predict income. How good did they do at that? Pretty good? Is there a number that I can quantify how good they did? Yeah, R squared. That is the proportion of variance explained by these three slopes of education, 16.4%. And if I unsquare it, that's R. So I can say the correlation between income as predicted by the model and real income is 0.4. Y hat would be the part that's in red here, leaving off the E. So anybody with the same level of education gets the same predicted income. So there's only so many possibilities given that. So beta 0 is the expected outcome, so income level here, for all of these predictors being 0. So I would have to know my coding scheme to know what that means, and I set it at 11. That's where they're all zeroed out. So at 11 years of education, people are predicted to make $8,530. Beta 1 is still a slope per year of education, but it's only covering the range of 2 to 11. So in that range, the slope is actually negative. Would I call it significant or non-significant? Based on the information shown here. Non-significant? What am I looking at? That is correct. P-value, yes. P less than alpha. So you would have set your alpha ahead of time. Missed a question from the Zoomers. Does the decision on when to use piecewise or quadratic come from visual inspection of the data? Yes, I think that you can estimate a mean for each unique value or rounded value of a quantitative predictor and use that as a decision tool to decide what kind of nonlinear function would work best. I also think it's important to take into the context of what it is about. So some piecewise slopes make more sense in certain contexts than others. Quadratic would make sense if it's something where it's going to go up and you expect it to come back down, or it's going to go down and you expect it to come back up. So all of those things I think you would want to take into consideration. So from 2 to 11 years, for each additional year of education, what happens? Do you make more money or less money with less? You lose about $270. Yeah, but it's not significant. Yes, I just got yelled at a conference this last weekend for interpreting non-significant slopes as directional. The reason I think it's okay to do that is because if you get enough of a sample size, like if you have census level data and you know how educated every single person in the country is, that's going to be significant. Power, remember that the ability to find a significant effect is a function of three things. More people, stronger signal, and a easier decision, lenient alpha. Right? If you're like, I think 20% is unexpected, it's easier to find something than if you say, I think only 5% is unexpected. But then you have a higher chance for type 1 errors. So yes, I'm paying attention to both significance level, which is a function of sample size, as well as the sign of the coefficient, because I think that's relevant for your reader to know. And this, by the way, this is a partial R. This is an effect size for this slope specifically. And it is very tiny, as you might imagine. Beta 2, I'm calling this an acute difference or a jump because it's just from 11 to 12. So it's still a slope in that it is a rate of change, but because there's only one possible change, it's just the difference. So if you graduate high school, relative to getting to 11th grade, you make $4,680 more. And I would call that, significant or not?
Significant.
Yeah, this one is like, what's my alpha though, right? If it's 05, significant. If it's 01, nope. And there is the effect size that goes with that one. And then last but not least, 12 to 20 has one linear slope covering it. That slope is 2.12, also significant and much larger. So for every additional year of education, among high school graduates, right? So that's within the high range of education, you get an increase of 2.12. And this is what it would look like, plotting the lines on here. So the slight negative slope from grades 2 to 11, the jump of about 4.68 from 11 to 12, and then for each additional year of education, income is predicted to go up by 2.12. Now, how well do you think this model fits this pattern? Are you happy with this? I'm happy. I'm half happy. I'm happy with this and I'm happy with this. I'm not happy with this. So I have some suggestions, right? If I really wanted to do a better job, I might divide this into further regions. So 12 to 15, that's like the undergrad version of ABD, right? Mm-hmm. Unless you got out in 3 years, in which case, good for you. And then there's a jump, like master's degree maybe, 15 to 16. And then it becomes a little more, I don't know. So I think you might need some additional slopes in that last piece. Yeah.
Could you do a quadratic if you felt it was pertinent, like after the 15, where it seems more curved at that point?
Yes, you could. You could also fit this slope squared in the model, and then make this one a bendy line. Mm-hmm. Yeah, you absolutely can mix and match. If you want the curve to be continuous at the knot points, you have to do extra work. But if you don't care about that, then you don't. Yep. Indeed. Yeah, okay. Do you want to see how to fit it? No.
Yes.
I'm gonna make you do it though. So
Okay.
when I put it that way, when I put it that way, example 3, continue. We only have a few minutes left, so the torture will end soon, I promise. Okay. So let me just show you how to make the pieces, because I think that's the trickiest part. So I honestly, when I have to do this in life, I build this table first. Like I build out what I want my code to do, because that helps me see the logic of how to write it. So there's more than one way to do this. The brute force way would be like, if it's 9, do this. If it's 10, do this. If it's 11, do this. But that gets repetitive and error prone. So I want to show you some more general ways to do this in both Stata and in R. So the first step in both, I think I can fit it on one slide here, make 3 empty variables. Okay, so I'm doing that in these 2 spots. The command in Stata is gen, it stands for generate, and then I'm initializing these variables to dots as missing. I'm initializing them to NA in R as missing instead. And note that I have example 3 as the name of the data set that shows up here. So less HS, grad HS, and over HS are the 3 variables I'm predicting. Then we have, let's do the Stata part first here. Replace, so remember, read these backwards. If education is less than 12, then replace less than high school with education minus 11. So that's going to do the same thing as a function, as opposed to if this, if this, if this. Because 11 is my centering point for the intercept. So I want to keep track of how far you are relative to 11. So subtracting 11 will do that for this column. But I'm only doing it if education is less than 12. So I'm covering just 9, 10, and 11 with that statement. And if education is less than 12, set the other ones to 0. So if we're up here, that's filling in these zeros right here. Then we do it again. This is greater than or equal to 12. Then the first one should be shut off at 0. The second one should go to 1. And the last one should be education minus 12. Because this last column here is how much past 12 you are in your years of education. Not 11, but 12, because this one covered the distance between 11 and 12. So figuring out how to do the functions, I think, is the hardest part of this. After that, you're pretty much home free. And then I have labels, of course. And then R, folks, yours is a little more complicated, but the if this part is the interior here, the whiches. Like that's the analog to if it's less than 12, then do this. So if it's less than 12, make a new variable out of the old variable minus 11. So it's that part is the same as in Stata, but only for the rows that qualify. it seems like it's redundant, but you have these two whiches that you need to do. So that is the trickier part. And then we initialize the other variables to 0 if it's less than 12, or we initialize them to 0 and 1 if it's greater than or equal to 12. And then education minus 12 out here. And that should be blue. All right, any questions on the code? And if you want to write it out longhand in terms of if it's 9, do this, if it's 10, do this, if it's 11, do this, if that's easier for you, go right ahead. It's just more work. But it does work. So once you have your slopes built, then the rest of it is pretty straightforward. So income again, here's my 3 slopes. This is stata output instead, so I'm trying to alternate rather than show everything twice. And here are the relevant numbers. What's that again? 3? Numerator degrees of freedom. And why is it 3? Number of slopes in my model. Yep. And denominator degrees of freedom. That's how many more slopes I could still add if I wanted to. What's that number? 159 tells me what? $159 tells me what?
The residual variance.
Residual variance for the win, otherwise abbreviated as mean square error or mean square residual. This is the amount of variability in income that we don't know why. It's unexplained. The original amount was 190. So relative to 190, we have reduced it by 16%. So that's where this R square came from. It's by how much did the original amount get reduced, this is what's left. Adjusted R square, that's the correction for adjusting for sample size. It's more relevant in smaller samples. It's not very different here. And root mean square error, that is the standard deviation of residual variance. So that's how wrong on average the model prediction is. It's off by $12,000. When you put it that way, it's like, I got 16% of the variance, but yeah, you're off by 12 grand. Like, that's not ideal. So all of these things would be relevant. Then we get into the coefficients. So if I get to 11th grade, that's my predicted outcome, 8.5, because that's when all my predictors are 0. And then here's the negative effect for less than high school. That's non-significant. The change of 4, if I do graduate high school, going from 11 to 12, that is significant if I have an alpha of 0.05. And then for each additional year of high school, or excuse me, past high school, I make $2,120 some odd dollars more, and that is also significant. Okay, how are we doing? Now let me leave you with a riddle, okay? What if reviewer 3 looks at this analysis and says, I think you don't need 3 slopes. I think 1 is fine. Prove me wrong. Could that happen? Yeah, it could happen. I want you to think about how I can come back to reviewer 3 with a justification for why I need 3 slopes. But you can come back and tell me on Thursday. How's that sound? Just let that percolate for a couple days. Or, look ahead and spoil your fun, but whichever.
Justify 4.
I could have way more than 3. I felt like I was being, pretty conservative by only having 3. So we will talk about that next time. And it looks like we are going to finish this unit this week. That's exciting. That just means I have to get more stuff ready for next week, so less exciting for me. But all right, let me know if you need anything. Office hours are back to usual this week. Homework's due next week. Thanks for being here. Happy Garbage Day. Bye, Zoomers. It is Garbage Day. And Coral